Yeah, under the supervising of Professor Isamu Akasaki, we have developed a new technology of crystal growth of blue LED materials, gallium nitride, and realized the P-type gallium nitride. That's our achievement.
Okay.
Yeah.
So, what is the importance of telling this type of stories for the new generation or for audience,
Uh-huh.
for all community?
Yeah, the blue LED can be used as a white LEDs or LED lamp system. The efficiency is very high compared with the conventional incandescent lamp or fluorescent lamp. So we can reduce the electricity consumption by about 7% in Japan, and in total much higher electricity can be saved in principle. That's very important. Yeah.
Okay. The importance of this type of success stories for a new generation, for students, to tell them about what you achieved in your life.
Oh, okay. Yeah, for young generation, my case, we are searching for what was interesting, what I should do. So I have tried several things, but among them, the blue LED was very fascinating, very exciting. So I'd like to send the message to the young generation that please find what the young generation are interested in and focusing on. The important thing is the concentration and focusing on each subject.
Thank you.
Yeah, thank you.
Good evening, dear guests, friends, interested person in physics. I welcome you to a really great event. I think this is the most important event which has been started here in the Kempinski Hotel. Before I start with the main idea of my short words, I want to give a short explanation about Kempinski Hotel. Maybe some of you are wondering why this scientific talk is given in Kempinski Hotel. I assumed that it should take place in the Geotech, for instance, or in the SKU. Why here? This I want to explain. Public talks have been a long tradition in the short history of the Geotech, and it started in the airport campus, and it was really nicely accepted by the citizen of Oman. But when we moved towards Hairan, then the numbers of participants dropped dramatically, and at the end of the day the audience was only consisting of the Geotech people, and this was frustrating for us, so actually we stopped. Then it was last year, I think last year or 2 years ago, so when Kempinski started to run, I had a meeting with Mr. Wiegand. He is the CIO, German as well as me, and we exchanged about our history and about things which we could share and where we could support each other. And then I explained my experience about public talks. And then we discussed this issue a little bit, and then we created a unique idea. The unique idea is the public talks are organized jointly by Kempinski Hotel and Geotech University, combining German hospitality with German system of education in technical and scientific way. So the Kempinski cares for the environment to make it as pleasant as possible for the audience. And when I have a look on this room and the corridor there, then I believe it is. And it is more nice environment than around Geotech, the Alban. It's not so nice. It will become nice, but in the moment it's more desert-like. And Geotech cares for scientific, outstanding and interesting talks given by people who are familiar with the Geotech, who belongs to the family of Geotech. as we have this evening. And I think this is a unique approach in Oman that demonstrates that a hotel is not only a building with some beds. A hotel can be more in an environment like the Wave and in Muscat. And the university has for sure to care not only for the students, but for the education of the citizen as well. So this is organized here. I think you understand, and when I have a look on your faces, I think that you are really happy with this approach. Thank you for the applause. Now, coming to the center of the evening, the public talk, which is given by Professor Amano. I will shortly introduce him, that you become aware about some data and his background. First, I have to tell you, Professor Amano had birthday today. So, happy birthday to you. So we will start with this kind of applause for your next new year, which hopefully will be scientifically outstanding as well. I'm pretty sure it will. I don't ask the audience to sing. I will do it later. So he was born in 1960 in Hamamatsu in Japan. And then in 79 he starts to study electrical engineer. So, contrary to some opinions, he is an engineer, and he went through the difficult education of engineering science. Then he made his master, and as I learned, at the end of his master and beginning of his PhD time, he starts to focus his work on the subject on which he was working for a couple of 10 years. That means the blue LEDs, the gallium nitride LEDs. And he did it. I think he will explain. So he needs a lot of force and patience and so on and so far to do this scientific work. Then after finalizing his PhD, during this time, he became research associate at the Akazaki laboratory, which is a famous laboratory in the environment of the Nagoya University. And then he starts the academic career, becoming an assistant professor at the Mayo University, then associate professor, and 2002 he became a full professor. So when you look on the timeline, it's not really fast. So it's a development according to the ordinary rules, nothing special, which learns to do excellent scientific work. It's not necessary to be a full professor. It's not necessary. You can do it even without being a professor. Then in 2010, he went to the engineering department in Nagoya University. 1 year later, he became the director of this famous Akazaki Research Center at that university. And he did his work. And now the top of the development was in 2014 when he got the Nobel Prize in physics. So an engineer got the Nobel Prize in physics, which is in a certain sense exceptional as well. The engineers are always claiming there is no Nobel Prize for us. Then we can recommend them do it like Professor Amano do. Go to physics, then you have the chance. In brackets, I can tell you, I did the inverse. I studied physics, and with my PhD, I moved towards the engineer. So now ask yourself, what is the consequence? Have a look on me. So my chance is now to introduce a Nobel Prize professor as a physicist who made the mistake to go to the engineering science. Anyway, I calculated, so he was 54, and So he was really young getting the Nobel Prize, because usually it is said you have to be 60, 70 years old to be in the state to get the Nobel Prize. So a young scientist. He will talk about the developing of the white LEDs, I guess, and then he will give some comments of his new approach. This is the Internet of Energy. Both are hot topics and very interesting. Enjoy. I really believe that you will learn a lot of things and you will be fascinated. Professor Amano, please, the stage is yours.
Your Excellencies, distinguished guests, ladies and gentlemen, good evening. It is my great honor to be here and give a talk. Today, I'm preparing two subjects. One is the development of could you change to the how the blue LEDs were developed in Japan. Yeah, I'd like to emphasize the leadership of my supervisor, Professor Isamu Kasaki. And also, I'd like to explain the present activity of our research center. Okay. So I appreciate the very kind hospitality of many people. Today I'd like to emphasize that especially for young generation, let's have dreams. Not our dream, but dreams. There are plenty of dreams. And try to realize. Okay. Let me discuss the future mobility in this country, Oman. We are thinking of the flying cars. Okay. Our colleague, Professor Yamamoto, just started the new program for flying cars. Okay. This is the model system for the flying cars. Faster fly. And then for high-speed flying, the wind angle changes too well. So the speed becomes over 300 kilometers per hour, which is much higher than the conventional vehicle system. Now it's only a model system, but in future we try to realize the brain which can move even the human. To realize such a system, we need a very good motor, very good motor control circuit system. And we need good transistors, especially the good transistors. And the good thing for our system is we don't need the long distance airport. By changing the angle of the wing, they control the angle and then going down so quickly. That's our dream. Yeah. My proposal is the flying car as the next generation major mobility in this country, Myanmar. Why? Oh, just a minute. Yes, please. Wing. Here is okay. Why flying car in Oman? Why not in Japan? Okay. In Japan, the houses are overcrowded. This is a photo of Nagoya, our city. Nagoya is not the biggest city in Japan, but even such a middle city, there are a lot of housing. So we don't have the space for experiments. We need an experiment space. That's why I would like to propose the collaboration with Oman researchers to establish a new mobility system, that's a flying car system in this country. Okay, the density of person in Japan is over 300 per square kilometer, but in Oman, it's still the number of population or the density of population is low. But some people are wondering why the blue LEDs changed to the flying cars. So let me explain the relationship between the blue LEDs and the flying cars. Okay. This is the periodic table of the element. We are using the crystals. Crystal means the element or atoms are arranged. One of the most famous crystals is the diamond. It's made of carbon, okay? And IC or transistors, LSI, it's made of silicon. But our crystal is the compound of metallic gallium with nitrogen. This is gallium nitride. So gallium nitride crystal is one of the compound semiconductors which can be used as blue LEDs, white LEDs, or even transistors. So let me explain the history of the development of these devices. Okay. Why the blue LEDs were developed in Japan? Yeah, I'd like to emphasize the strong leadership of our supervisor, Professor Isamu Kasaki. This material were performed, the research in 1970s all over the world. Very famous professor trying to commercialize the blue LEDs based on this compound semiconductors, gallium nitride, but abandoned in 1970s. The reason is it was very, very difficult to get the good quality crystal. Yeah, in our field, we say the growing crystal. Growing high quality crystal was very, very difficult. And also, for efficient LEDs, we need both N-type and P-type. Unfortunately, no one succeeded the P-type gallium nitride. That's why the many famous researchers abandoned the blue LEDs, except one person, Professor Isamu Kasaki. Yeah, he started the research from 1967, over 50 years ago. Okay, and he changed the crystal growth method. Okay, for a long time. Yeah, but at that time, he was belonging to the private company. It it's Panasonic. But he couldn't get the products for money. So unfortunately, the manager of Panasonic decided to abandon the research of this material. So he had to move from the private company to the National University in 1981. And I joined his group as the undergraduate student. When I saw the graduation research nitride-based blue LED, I was so excited because at that time I was interested in the microcomputer, now PCs. At that time, all the people use this type of displays, brown tube or CRT, which was very big. So if I could achieve blue LEDs, I could change the world as the innovator, and that's why I could concentrate on performing the research on blue LEDs. The problem, there were many problems, among which the most serious problem is the shortage of the research funding. And, why it was so difficult to grow high-quality gallium nitride? Yeah, we need the bulk, big crystals. To grow gallium nitride crystals, we need a very high pressure, 45,000 atoms, and high temperature, over 2,500 degrees C, which is almost similar or even difficult compared with the diamond. So we have to grow the thin films, but there is no gallium nitride crystals, so we have to use the foreign materials like sapphire. But the arrangement of atoms is quite different. The difference is over 16%. In general, this is called the lattice mismatch, should be less than 1%. So 16% is almost impossible to grow crystals, okay? And the most serious problem is the shortage of the funding. Okay. When Professor Akasaki moved from the private company to the National University, the research funding per year is 11,000 real. To grow the gallium nitride crystals, we need at least 350,000 real. But we don't have such a money. So students, Dr. Koide and me, established our own crystal growth system. It's 10,000 real. Okay. Yeah, the reason why the blue LEDs were invented in Japan is, first, the strong belief of Professor Akasaki's to this material system, gallium nitride, and also his power of involving the surroundings, like me. Okay. In the laboratory, nobody knew about the new crystal growth system, that is MOBPE. So even the beginning students like me could freely discuss with Professor Akasaki. So students could independently proceed the experiments, so I tend to feel the responsibility for their research result. So I'd like to emphasize again why the blue LEDs were invented in Japan is the strong leadership of Professor Akasaki. The belief of the materials and the power of involving the surroundings. Okay, I'd like to emphasize that how Blue LED change your lives. The reason why you enjoy the smartphone, it's full color. The reason is because of the emergence of Blue LEDs. And why Blue LEDs are so important? Only blue can realize white like this. Okay? This is Blue LEDs. The LED lamp is composed not by the blue, green, and red LEDs, but white LEDs is composed of blue LEDs with this film. Okay? We can easily realize white with this combination. And also, blue can realize green or red. Okay? Blue can realize green or red, but green or red cannot realize blue. Okay? Only the blue can realize every kind of colors. That's why the blue LEDs are so important. Okay? Yeah, by using the LED lamp, which is very energy efficient, so we can reduce the electricity consumption a lot, 7%. We can reduce the total electricity consumption by about 7%, which corresponds to 3.6 billion real, which is a huge money we can save. And more importantly, LED lamp help people from the fear of darkness, like Mongolian people who continued the nomad life. This is the LED lamp inside the Mongolian tent gel. So that's my Blue LED story. So the research of the Blue LEDs was finished. So I searched for the new research subject. And I visited San Diego National Laboratories to find a new research subject as a sabbatical. 3 months. Okay. Before visiting San Diego National Lab, I had thought that I would be superior to them because at that time I thought that we developed a Blue LEDs. Okay? But soon I found my mistake when I visited San Diego National Lab. During 3 months sabbatical, I learned a lot about very high creativity and the sincerity of San Diego peoples. So I changed my mind. I heartily decided to contribute to mankind even more than them. But how to do that? So I found the new research subject, that is the ultraviolet LEDs for providing drinking water. Okay. According to UNICEF, still 844 million people lack even the basic water services, and 2.3 billion people lack even the basic sanitation services. Here, to start the UV LED research, I faced the similar problem, that is the lack of or shortage of the research fund. So I applied to the Fundamental Research Fund, the Ministry of Education, or JSPS, and fortunately I got the research fund. But the problem is my research fund was not sufficient to purchase a new crystal growth reactors. So I visited the company provider, the Epic West, and finally they agreed to supply us with a very reduced price, the new MOVP reactor. And we also have the problem of the shortage or lack of the spare parts. We have to use the very special spare part, that is tantalum carbide, which is very, very expensive. So I visited the private company Eviden, and they agreed to give us, with a free of charge, the new spare parts. Then finally we succeeded to grow world's highest quality crystals. Then as a next step, we applied the applied research fund to the Ministry of Industry. So we got a large amount of fund. Then we succeeded to fabricate world's highest output power, the ultraviolet LEDs. And then the technology was transferred to the private company Nixo and the UV Craftery, and they were funded by the private bank. Now we succeeded to manufacture the UV LED-based water purification system. World's biggest UV LED drinking water supply system is realized by the private company MetaWater. This is the world's biggest water supply system. It provides 1,200 cubic meter per day for 3,500 people. And also, it's a high dose. It damages even the cryptosporidium, which is strong bacteria against the chlorine. And one of the most advantages is a long lifetime, 45,000 hours. It's longer than 5 years. In conventional drinking water supply system, the conventional lamp, mercury lamp, was used. Their lifetime is shorter than 2,000 hours, which means shorter than 3 months. Okay. That's the story of photonics, the LEDs. Then I would like to switch to the present activities. We call our activity the transformative electronics for realizing the zero emission society. Let me explain the word transformative electronics. Okay. For example, the role of electronics is photovoltaic or solar cells. It transforms photon energy to electrical energy. Okay? And the LED lamp transforms electrical energy to photon energy. So the role of electronics is the transformation of energy. And all the students, if you run the physics, the maximum transformation efficiency is, of course, 100%. Okay? We cannot overcome the 100%. But we are aiming at transformation efficiency over 100%. Okay? Let me explain the reason why. For example, the solar panel, the power efficiency is still lower than 50%. And more serious is your smartphone or your TV, your PC display system. Efficiency is very, very low. Only 5% at most because of there are so many filters, color filters. But if you watch the TV show or the movies, emotional energy is countless. Okay? That's why we are thinking of the meaning of energy efficiency over 100%. Okay. Yeah, it's half joke, but half serious. Okay. Let me explain the more serious thing. The Japanese government targeted an 80% reduction of greenhouse gases, especially the CO2 emission, by year 2050, like this. That's a very challenging task. But it seems to me no politician considers seriously to realize that. But yeah, we are engineers, so we consider very seriously to realize the 80% reduction. So we follow the Professor Kaya's identity. According to Professor Yoichi Kaya, the graph alone, the total emission, CO2 emission, can be written in this formula. The P is the population. By year 2050, the population of Japan will decrease to almost three quarters, 74%. But the productivity of each person will increase about 50%. So GDP per person will increase about 1.5. So with these two formulas, we have to expect the increase about 10%. So we have to reduce these two terms, energy per GDP and the total emission per energy. This term is the efficiency of final product, like an electric vehicle, TV, and also this term is the primary energy. If we can reduce to 60% and 30% for each, we can realize in total 20%, which means 80% reduction of CO2 emission. But we are the engineer, like you. So we consider seriously how to realize that. So we estimate the cost of the CO2 emission reduction. Yeah, we have to change the energy, the oil, sorry for many people, but oil or the natural gas to renewable energies, okay? For example, increase of solar panel, the cost is 5.2 trillion Japanese yen, which is very expensive. But in case of renewable energy, only the solar panel is not sufficient. The peak solar panel power generation is in the noon, but peak of the usage is in the evening. So we need an additional system, that is energy server or the batteries. Okay? So we have to consider additional cost of the energy server. It's almost the same, 5.2 trillion Japanese yen. So in total, we need to pay 10.4 trillion Japanese yen to realize solar or renewable energy-based system, which is very, very expensive. But we consider to realize this system, we can take 20 years. So 10.4 trillion divided by 20 years, it's 500 billion Japanese yen, which is 0.1% of the total GDP in Japan. Only 0.1%. Okay. So the engineer, like me, believe that it is possible. So we expand this idea to realize reduction of CO2 all over the world. In IPCC fifth assessment, it is claimed that average temperature increase should be less than 2 degrees, which means that we have to reduce the CO2 emission 50%. Okay. So, no clear scenario, CO2 emission increase. So, we have to follow the 2 degrees scenario. According to this report, it is possible to realize by year 2080 to 49%, or almost 50%. Okay, but our goal is 2050. Okay, so if we realize 30 years ahead of schedule, we will achieve 50% reduction of greenhouse gases emission. That's realizing less than 2 degrees increase. Okay, how much do we need? This person estimated the cost of CO2 reduction, the GDP ratio, 0.33%. If we pay the 0.33% additional money, we can realize the reduction of 50% CO2 emission. So we would like to propose that our new transistors can realize such energy saving and the CO2 reduction system. For example, we are proposing the new solar power on the sea. Okay. The problem in Japan is the cost of land is very, very high, very expensive. So we would like to propose to use the sea. Okay. And by mobile system, it becomes environmental friendly. And also, for electricity grids, we are proposing a new system that is wireless power transmission system. We can charge to the electric vehicle even during driving. Why it is necessary? As I mentioned before, the peak power generation of the solar power is in the noon, but the usage peak is in the evening. So we need additional power energy servers. But if we can charge while driving, we can reduce the cost of energy server. Okay. We need at least 490,000 quick chargers if electric vehicles are popularized, okay, which is substantially large numbers. Okay. To realize such a system, we need an AI control system and high-speed intelligent power conditioners to control the electricity to energy server or the electricity grids. Okay. New generation electricity grids, it's a wireless power transmission. Yeah, I'd like to show some demos. This is the transmitter, and this is the receiver. We can transmit energy wirelessly from this metal over this metal. It's made of aluminum. It's very, very inexpensive. Yeah, by using this system, we can realize the emergency helicopter power transmission, disaster rescue robot, power assistant robot, especially necessary for the aged country like Japan. Okay? And healthcare, there are many, many sensors inside our body. And industrial robot, we can operate 24 hours a day. And of course, electric vehicle, charging while driving. And also, finally, we are planning to transmit the electricity to flying drones. So, next, I'd like to discuss the reduction of electricity consumption by improving efficiency of final products. Compared with the primary energy system, the cost is much, much lower. So that's a good chance to invest to these compound semiconductor systems. Yeah, the LED is very energy efficient, but the percentage of the total electricity consumption is only 14%. More important is air conditioners or refrigerators, the motor-driven system. To control the motors, inverter circuit, this is the inverter circuit. Electrically driven control system is very, very effective to reduce the electricity consumption. This is the mechanical control, and this is the electrical control. The same airflow compared with the mechanical control, we can reduce the input power a lot. And for using the inverter control, Japan company has the advantage. In Japan, already 100% inverter control is used. Okay? The Asia, it's very low. So please check your air conditioning system. But even using the inverter control, we have the large loss. Yeah, consider that. Please consider that if you use the solar panel on the roof to operate the PCs, solar panel generate DC power, but at home you are using the AC power. So we have to, you have to transform the DC power to AC power by using the power conditioner. You have 5.5% loss. And there is a AC adapter, 7% loss. And inside the PC, you have to control the DC voltage, 5% and 12% loss. So in total, even though you generate 82 watt, you can use only 60 watt. So about a quarter of the generated power is lost. So we are proposing to replace the conventional silicon-based transistors to gallium nitride-based transistors. Okay? The gallium nitride is stronger than silicon by a factor of 10. So we can reduce the size of the device to 1/10. So automatically, the loss is 1/10. So we can reduce the total electricity consumption by about 10% by replacing silicon-based transistors with gallium nitride-based transistors. Okay, so we should consider how to realize fundamental research to innovation or change the social system. So we are proposing eco research system. We established a new consortium. Now it's an open innovation platform. 50 private companies, 21 universities, and 3 national research institutes join our group. This is the system to overcome the death barriers. And our approach is really a top-down approach. We consider the application first. Electric vehicle, trains, the ships, and in future, the flying drones or flying planes, or Internet of Energy or Internet of Things, 5G or post-5G wireless communication system. We can realize all such a system by the gallium nitride. So we consider the system first. Then we consider the module and the module experts. And we consider the device and device experts and the crystal experts. It's really a top-down approach. It's quite different from the previous R&D model in Japan. The previous R&D model, it's a general purpose products. So from the bottom, R&D, epitaxy process R&D. So it took a long time to finalize or to reach to the system. So our new R&D model is a customized model. Yeah, our collaborator are performing a very, very fundamental research to simulate the crystal growth from the first principle calculations. This is the simulation of this yellow circle is a gallium atom on the gallium nitride surface. Yeah, this is the first principle calculation based on the quantum mechanics. And we found that gallium atoms forms a gallium metal, one monolayer of gallium metals. And this is the gallium nitride and gallium metal react with ammonia, Na3. So this ammonia react with the top metallic gallium like this. So we can develop a crystal growth simulator based on the first principle calculation. It's an ultimate simulator. It's a very fundamental research. And another collaborator, Professor Yamamoto, he delivers the world's highest efficiency inverter for electric vehicles. Conventional electric vehicle, the silicon-based transistor was used, so the loss is very large. He realized the efficiency over 99%. It's almost 100%. Then another professor, Professor Shiozaki from the Toyota, used Professor Yamamoto's modules, inverters, to the real electric vehicle. This is called all-GaN vehicle, which can be shown at this year's the motor show in Tokyo. If you are interested, please visit the Tokyo Motor Show. You can see our model in which the all gallium nitride inverter is used. It's the world's first application of gallium nitride inverter to the electric vehicles. So our next target is, as shown before, the flying cars, the SkyDrive or regional mini jet or regional jet. The Toyota or Symphonia Technology or Mitsubishi Heavy Industries are collaborating with us to realize a next generation motor-driven aircraft. So in Nagoya University campus, we developed a new clean room specially designed for gallium nitride device. This is the floor, and we can provide the chip service or wafer if you are interested in, with a very reasonable cost. For transistors, the cost, the price is like that. And the laser diode, we can also provide the laser diode if you are interested in. One of the most serious problems in Japan is the aging. By year 2050, the aging component becomes like that. Many elder persons. So we would like to support the elder person, the air taxi or air commuting system or pilotless drones for logistics. That's our dreams. Okay. Finally, I'm not sure whether we have time. Finally, I'd like to explain our program, educational program for graduate students. It's one of the Ministry of Education doctoral program for world-leading innovation and smart education. Our program is called the DII, Collaborative Graduate Program for Accelerating Innovation in Future Electronics. D stands for the deployer, which is entrepreneurs. I, innovator, who develop the production technologies, and I, investigator, who invent new technologies. This is based on my experience. In case of blue LEDs, it took 30 years from the invention to innovation. So if the student having the different talent, different potential, deployer, innovator, and investigator, gathered and performing the same research, maybe we can reduce the period of innovation from 30 years to less than 10 years. One of the advantage or the characteristic of this program is not only the faculty of Nagoya University or overseas support the student, but also the company people. Company people join this program as the mentors. Okay? So overseas, Nagoya University, and company person act as the mentor of each student. So it's an independent degree. In addition to PhD, we will provide the DII certificate for collaborative graduate program. It's very heavy. Yeah, we have just started, and we visited, or the student visited National University of Singapore, so they enjoy the atmosphere, not only the atmosphere of Singapore, but also they consider very seriously the startup, how to realize a startup, new companies, based on the cutting-edge technologies. So if you are interested in the work we are doing at Nagoya University toward achieving a sustainable, smart, secure, and safe society, please do not hesitate to contact us. Our staff is joining this presentation. Thank you so much for your kind attention.
Thank you, Professor Amano, for your for the opportunity that you gave us, for sharing all your knowledge with us. Thank you, Your Excellencies, Director Generals, and distinguished audiences for coming today with us. I would like to open this stage for questions and answers, of course, by Professor Amano. Are you giving us 10 minutes or 1 hour?
As long as.
Okay. I would like to start by receiving the first question from our youngest audience. I would like to call the youngest audience, I think, Salim. Salim is, among other friends, coming from Finland Oman School. Finland Oman School is, I would say, is a new baby of Oman Educational Services. And we think of Geotech as being the big brother, and they are the small brother. Salim, you would like to ask a question to Professor Amano? I believe you made lots of research to find out today that his birthday, and I believe your friends prepare a poster for him. Yeah? Okay. So what is your question, please?
My question is, what problems, did you face any problems while creating the LED lights, the blue LED lights?
Could you repeat once again?
What problems did you face while creating the blue LED lights?
For LED lighting. For
The problems and the challenges.
For problem and the change. Oh, okay, I see. Yeah. When I was a student, yeah, I was searching for what I should do as the researchers, so I could concentrate on the performing the experiments. So there was no problem. Yeah, I could do experiments all day. 364 days per year. And I could continue the research, the experiments over 1,500 times. So as concerns the performing the experiments, there was no problem. The challenge is funding, yeah, of course, funding. And also, yeah, at that time, all over the world, no one succeeded the crystal growth and P-type. So sometimes I was worried about whether the direction is correct or not. We consider every day. Or, for example, I did the experiments 5 times, at least 5 times a day. So I was so tired. In the midnight, I went back from university to my home. So I was so depressed and wondering whether my decision was correct or not. But when I wake up in the morning, next day, many new ideas come to my mind. So in the midnight, I faced the worry, but next morning, it disappears. New ideas came to me. The continuation of such challenge, that's one of the reasons why we can overcome the problem. Okay?
Thanks for giving me the option. Thanks for giving me the chance to answer, to ask you the question.
Thank you.
And happy birthday.
Oh. Thank you.
Any more questions?
Assalamu alaikum. Thank you for the wonderful lecture. I have 2 questions. the question number one, considering that the first model of the GNU all cars, the car which will be shown on 2020. So shall we consider that the research on the new transistor already being completed, or is still there is more research to come? So the question, in other words, when we will see the GN transistors replacing the silicon in the commercial scale?
Yeah, the first question, the point
Yeah.
is...
So it is the same. The first question is when we will see the new transistor replacing the silicon on the commercial scale, considering that on 2020 it will be shown in the first car on the Japan.
The new transistors. Oh.
So the research have been finished or is still ongoing?
No.
Okay. So the second question, when I look around your name on Wikipedia, I found that your laboratory being called the No Light Castle, which means you've been working for quite late at night. So the question is, at the average hours, how many hours do you sleep per day? Thank you.
As concerns for first question, yeah, we succeeded to demonstrate it's a very initial stage of the transistors. To use the transistors to, for example, the electric vehicle, the safety issue is very, very important. The failure is less than 0.0000%. Yeah, it's very, very serious. The silicon transistor can realize that, but it took a very long time to realize such a reliable system. Yeah, our transistors still in the very preliminary stage. The efficiency, performance is good, but the more important is the safety issues. So we are trying to check or characterize or confirm that the new material transistors is safety. That's the most important issues for us today. And for working hours, yeah, there is a very strict regulation now. So when I was a student, I can stay in the university for a long time. But now it is prohibited. So I have to go back before 10 o'clock. At night, yes.
And you arrive when?
Arrive 7 a.m. No, that's okay. Okay, thank you.
Thank you. Your Excellency, you have a question, I believe.
Oh,
Thank you. I have two questions.
yes.
The first one is on this wireless transmission of electricity. What's the electricity loss? Because even if you transmit on conductors, you're losing
Yes,
about
yes, yeah, of course, yes.
4%. So there
Yes,
must be.
yes.
So that's the first one.
Yes.
The second one is deep inside me, I truly believe that tomorrow's problem cannot be solved with today's technology. Even if you fill kilometers of the beach with solar panels, you're only expanding what we know today. Yeah, there is nothing in terms of innovation for a new way of generating energy. So we can put kilometers and kilometers of solar panels, wind turbines, and whatever is traditionally available today.
Yes.
But it's not going to solve tomorrow's problem. So there must be some sort of breakthrough. And the question to you is, what is that breakthrough
Okay, I see.
that we need to start working on today in order to realize the 2% by 2050, which in your chart, it's not possible at the moment.
It's a specialist question or the suggestion. Thank you so much. A very important suggestion. First question is the efficiency of the wireless transmission. It depends on the distance. In case of the short distance, for example, the charging to the electric vehicle, the distance would be shorter than 20 centimeters. In such a case, we already realized the efficiency 92 or 93%, but still the 7 to 8% loss compared with the wired transmission. Okay. And the problem is the long distance transmission, especially to the drone. Drone flies from 60 meters to 120 meters. In such a case, the efficiency is still very low. It's limited to transmitter but the receiver. The receiver efficiency is, at present, it's lower than 40%. And with increasing the distance, the efficiency drops sharply, even using the microwave. That's a problem. And for the second question, yeah, we are discussing with the specialists for electricity grids. And according to them, DC transmission is better than AC transmission. So we are considering how efficient is the DC, high voltage transmission. If we can increase the voltage to higher than 10 kilovolts or higher, we can reduce the electricity loss of the transmission from the ocean to the land. But still in the preliminary stage, we are now simulating which system is the best for transmit the electricity from the long distance. So
My question was more on the
generation. For generation, the solar power. If we use the silicon-based solar power, the efficiency is 25% maximum. For much higher efficiency, we have to use the stacked or tandem cell or the March junction cell. The problem is it is too expensive at present. If we use the March junction solar cell, the germanium, indium gallium arsenide, gallium phosphide system, it can be used only for space applications at present. And so we have to consider the cost of the building rather than the efficiency. If we can reduce the cost to 1/10, we can realize the renewable energy-based system. So the cost is more important than the efficiency at present. Okay?
We have a question over there, then we come to Professor Modigel.
Thank you, Professor, for the enlightening presentation. My question is about the center that you have there, where you have companies working with universities.
Yes.
I'm interested if you could really shed some light on the model, how you manage to bring companies which are in the competitive domains to work with researchers who are really on the collaborative domain.
Yes.
How you are really managing, who initiate the ideas, and how to manage the IPs and the output of that process.
Yeah.
So if you could really highlight on that, thank you very much.
Thank you. That's a very important point. Of course, there are many companies which are sometimes very competitive companies join our group. Like, in our case, the Toyota and Nissan are joining our group. But the good thing is, still, the gallium nitride transistor is a very initial stage. At the initial stage, they help each other. It's an open innovation stage. Then, if it is established, maybe from the second level, it becomes a competitive stage. So they perform the development by themselves. So our center is focusing on the very initial stage technologies.
Professor Mudigal, you have a question?
Yeah. As far as I know, the lithium is the most prominent element on the Earth. But gallium is really rare. So when we apply the gallium for the transistor and for the light emission diodes, then isn't there the possibility that we run out of gallium and then?
The gallium deficiency?
Yeah.
Yes. Okay. Yeah, the gallium is, we can get gallium from the bauxite. It's an aluminum source. Okay. And as concerns the gallium concentration, we can expect 2 orders of magnitude, large amount of gallium from the mount in Guinea and mount in the Australia. So we don't need to worry about the deficiency of gallium at present.
Thank you.
Yeah.
الصف الأمامي عندهم واسطة شوي. Professor, thank you very much. I liked actually the movie you started with for your first visit to Oman, where the speed was over 108. So I think also you have realized that Muscat itself, especially, been lightened with no LED in the roads.
That's a problem here.
So, and I also have heard about one of your projects helping some countries converting the street lighting to LED. So from rough calculating, what you think Oman as a country can save energy with LED in the streets?
Yeah.
So this is number one. Number two, you've talked about the converting inventions to innovations.
Yes.
Took, for instance, your project 30 years.
Yeah.
So what do you think the role of what's so-called academic entrepreneurs?
Academic
Entrepreneurs. Entrepreneurship.
Entrepreneurship?
Entrepreneurship.
Yeah. Oh, I see. Yeah, for the street lighting, yeah, that we have already a good system. The combination solar panel with the street lighting. So please use new system. Yeah, it's very bright. And also for entrepreneurship, yeah, compared with for example, the Stanford or the Silicon Valley or Shenzhen in China, the activity of startup still in the preliminary stage in Japan. So we are trying to encourage the young students and young researchers to start the venture or startup companies. So our DIA program, we are preparing the lecture for startup, and the people in the startup company join as a mentor. So we support the students to start the new company. Okay.
Another question from our young audience. I would like to call on Anas from grade 8 from Finland Oman School. He has a question.
Did you have any device for students who like to research?
Could you repeat once again?
Very good question. Do you have any advice for students interested in doing research? So he wants your advice.
Advice? Yes. Wow. Okay. So please perform what you want to do, what you are interested in. Yeah, you have the chance. How old are you? Well, it's very, very young. Maybe you have the chance twice as much as my case. So my advice is to perform what you are interested in and what you want to do. Okay?
Thank you. I would like to give the chance to another member from the audience. I think it's a young one also. Yeah, Fatma.
First of all, thank you for your interesting lecture. My question is, in your slides, I noticed that there is a lot of numbers. When you did your research, were you focused on reducing the price, the cost of electricity, or to improve our lives and with this new innovation?
My case?
Yes.
Yeah, well, when I was a student, I never considered the decreasing the electricity. I was only interested in the blue LEDs for display applications. So sometimes the achievement and application becomes different. Okay.
Thank you.
Yeah.
Thank you so much. I'm going to take the last question. Please go ahead.
I would like to thank you for your very informative lecture, and I would like to ask you about the difference between the conventional molecular beam epitaxy, crystal growth, and between the reactor that you have came up with. What's the key difference? Is there a difference in the lattice structure, or it's just a matter of the cost and the final process?
It's a very sophisticated question. Yes, that's a very good point. The reason why I showed the result of first principle calculation is we are trying to develop a new types of crystal growth system based on first principle calculation and AI controlled system. Okay, by using the first principle calculation combined with the fluid dynamics or thermodynamics, we can realize truly the simulation with the atomic level simulation is possible. We believe that's the ultimate goal for the design tools for the new crystal growth system. So that's why we are interested or focusing on the first principle calculation-based simulation for crystal growth. Okay.
Thank you, Professor Amano. Thank you for giving us the chance to know more about your life-changing invention. Thank you, our valuable audience. And I would like to call on Your Excellency Abdelmunaim Al-Hsani, our guest, on the stage to give, on behalf of us, to our Professor Amano gift as an appreciation, as a token of appreciation. And I would like also to call on Dr. Hussein Salmi, the Deputy Director for Administration and Finance at the Geotech, on stage.
Oh, oh, great. Thank you so much. Thank you.